the static loading is still important, right? Static loading was very important in the earlier times, perhaps in the 19th century, when there was no cars and no engines and nothing which was, everything was human driven, right? Like a animal driven, like a horse or so on. But so static loading was important. The 19th century. And this was useful because we had slow speeds. Things moved slowly. There were light loads. And then we were fine with having a large factor of safety. But what changed principally was that we started worrying too much more about dynamic loading. And that happened with the sort of the Industrial Revolution, when there was, started with the steam engine. So once you have an engine and you have something doing work for you, you are typically looking at fast speeds, higher load, and of course, cyclic loads. Okay, so once we have high-powered machinery, we have all these things, and once we have all these things, we need to worry about dynamic loading. So what's the key difference? Well, it turns out that if something fails at, let's say, load P during static loading, it'll actually fail at a much lower load if the same load is applied in a fluctuating way. So if it say load fails at 1,000 newtons, it'll probably fail at 600 or 700 newtons if the stress is repeated. So that's why we need to worry about dynamic loading, and that's this whole chapter is devoted to that. So machine elements fail at a lower load when subjected to cyclic or fluctuating okay, so that motivates the need to have theory of failure when elements are subjected to dynamic or cyclic or fluctuating loads. Okay, now there are three main methods of doing this. Fatigue 5 methods. There is what is known as a strain life method. Okay, it's basically something we'll not cover in this course, but it is to do with use crack nucleation to predict failure. Okay, so when things fail, you see that well, microstructure for any element is like there's a certain microstructure, and when you look at the material when it's about to fail under a microscope, you'll see that there's a beginning of a crack growth, and that is when you know that it's going to start breaking in a certain place where there will be high stresses. And so this theory basically looks at crack nucleation at the beginning. Nucleation is also the beginning of the crack in order to predict failure. This is something which you can study in a higher course in solid mechanics, so we'll not do that. There is another method called linear elastic fracture mechanics. Fracture mechanics. So this one uses the crack propagation to predict failure. So as I said, once the material is loaded, the cracks appear, and those cracks grow in certain direction. Based on that crack propagation, you're able to predict failure. Okay, both these 1 and 2, you can cover in an advanced solid mechanics course. Okay. What we'll do is we'll not do 1 and 2, we'll do 3, which is known as the stress life method. This one is sort of in line with what we've done so far. What we've done so far is taken the material, loaded it to failure, created curves to understand how failure occurs, and use those curves to make queries and predict failure, right? So we'll use this method, use empirical tests based on loading test specimens in order to predict failure. Okay, so we use this approach 3 in this. So we really don't need to know how cracks occur, how they propagate. We really don't bother with that. We just say, we know how things are going to fail. We take a test specimen, we load them, we make plots which are representative of failure, typically the stress and the number of cycles to failure. And from that, we can predict when some material will fail, if it is actually put in a scenario where it is a part of an automobile or a ship or a train or whatever. So let's do number 3. Okay, so as I said, this is based on test specimens. So yeah. Yes, that's right. So this the meaning to that. So here is an example of a test specimen. Okay. So we are 607. So the stress life method and diagram. Okay, so far we've only seen tensile loading. This is not loaded in tension, it's actually loaded in bending. So how is it loading in bending? So what we can do is, we know the specimen, this is a free body diagram of the specimen. You can see the forces, you know the distances. We can draw the shear force diagram for this, just like we've done shear force diagram for other things. So we can see from the left to right, there's a force F, right? So it goes there, it comes down because there's a F downwards. And then the force is 0. And then this force would be negative out here, and then 0. This is minus F. And this is a, okay, so the thing to notice is that between those forces F, which act downwards, the moment is constant. Okay, this is also known as a 4-point bending specimen, very commonly used in testing. The nice thing about that specimen is this kind of loading is that the moment is constant. So you can be certain that those moments can be used to validate any theory which involves uh, pure bending in the middle part of the beam. So we can recollect that sigma is my divided by I. This is the stress in the middle portion, right? And m is F times A, y divided by I, because that's the moment. So what we do is that's the moment. What we'll do is, in order to simulate cyclic loading, we'll actually let the force vary. It would not be constant. We'll just make F go from negative minus F to plus F, minus A to plus A, and in a cyclic fashion. Okay, so zoom. So let's F equals F0 sine omega t. We can sub that in this equation, and we get this cyclic load. So I'll rewrite the equation. So we have F0 sine omega t times A y divided by I. And so we can just club all the terms not involving the sinusoid together. And I'm just going to call that term, which comes as the amplitude, as sigma 0. So we have sigma equals sigma 0 sine omega t. Yeah. A is the distance between between F and F. It'll appear as the moment. Yes, it's along X. So this is a cyclic loading, as you can see. So what it means is that if you now plot sigma as a function of t, then you should see something like this, right? A sinusoid with amplitude sigma 0 minus sigma 0. So let's say it starts here. Then when it reaches the first cycle, so this will be first cycle number. That is, it is fluctuating load. That's the first cycle, and then we can keep going like that. That will be second cycle. So what we're trying to do is, when predicting failure, we want to predict the number of cycles to failure. So cycles to failure, I'll use the abbreviation N for a given amplitude. Okay, so what's going on is this is subjected to cyclic loading. We want to predict. So let's say that we know that the automobile part is going to be subject to certain stress. Let's say 10 megapascals. Okay, so then that automobile is going to run for so many cycles, right? It's going to run maybe 10,000 cycles. We want to figure out at what cycles, at 10,000 cycles, for example, will it fail or not? If it doesn't fail, then we want to perhaps go to 15,000 cycles, 20,000 cycles, 30,000 cycles, so on. So we want to predict n for a given load at which failure will occur. And that's the whole purpose of fatigue loading. Now, there's a video I wanted to show you, which I think is,
emergency stop button on top of the ET2.
Okay, so that's the loading of the specimen.
After removing the safety shield, insert the sample into the drive side and use the provided wrench set to tighten it.
Okay, the load is actually below.
A specific amount of weight to the hanger to generate the required bending stress. The formula for determining bending stress is provided in our documentation. Once determined, load the weights onto the hanger. On the back side of the spindle drive.
So the key thing is that this is how the load is applied, and that load is constant. Here the fluctuations come because it's being rotated. Okay? So one way is you can rotate the specimen and then keep the load constant. The other way to do this is to keep the specimen constant and then apply a load which is fluctuating, which I think is hard to do in the specimens. There are other ways. This is one of probably the older setup, but there's a newer setup where you're applying a bending moment directly, you're not really applying it through the waves like that. And you can just search for rotating beam, fatigue beam experiment. You'll see these examples. So as you saw, we chose sigma 0, and that sigma 0 here comes because of those weights. So you can add more weight. Then keep increasing the cycles. And till failure. So this is actually a very time-consuming experiment because what I'm showing you is this. So for example, here we fixed a particular load stress. This is the stress on the y-axis. And then we keep increasing the cycles till it fails. So here it fails at I don't know, 10 cycles. Okay, that specimen has broken, you discard it off. Then you apply a new stress, a new value. Let's say this is sigma 1, sigma 2. You keep doing that, you increase the number of cycles till it fails. That failed at, I don't know, maybe 250 or something like that. So you discard that sample. You keep, you take another specimen, you just do that. You just keep doing that till, and all those dots correspond to a broken specimen. So you can see it's expensive and very time consuming because all those dots are one single specimen. So once you generate this curve, you can now start using this curve for a different material. I mean, not material, but different design, but the same material because this is specific to the material. So you have to do the same test for a different material. This is, I think, for steel. What we can see here is that there are these regions. So on the y-axis is the stress, the x-axis is the cycles, and what you see is there are like three regions: low cycle fatigue, high cycle fatigue, and within high cycle fatigue, there's finite life and there's infinite life. Okay, what this means is this: when the stress is high, okay, when the stress is high and you have no cycles, 10 raised to 0 is 1. That means that it's not fluctuating; it's just stationary. That's the maximum strength you can get. So that's what we did in the previous chapter. That's the maximum strength of the material. The moment you start increasing the number of cycles, you see that it fails at a lower sigma, right? Which makes sense, right? Because if it's fluctuating, then that's giving it more stress than it would without fluctuations. And then as you keep increasing the number of cycles, you'll see that the stress which the material can withstand keeps decreasing. Okay? So this is 10,000 is like 1,000 is like a ballpark number where they consider that to be low cycle fatigue. So anything between 1 cycles, which is 10 raised to 0 to 1,000 is low cycle fatigue.
So you said each point was
Yes. So beyond 1,000, you can see that the stress which the material can withstand sort of decreases much more rapidly than the first part. You can get that sense from the slope. So the slope is sort of shallow for the red line I drew. It's for the blue, it's much more steeper. So the stress which it can bear rapidly decreases up to 10 raised to 6 cycles. So that region is considered to be sort of high cycle fatigue. And then you'll see that at some point beyond 10 to 6, this region, it's infinite life, which means that it will not fail. You don't see any points here. So what this is saying is that if the stress is low enough, here it's called SE, then the material will not fail. It'll just go for infinite life. So something like this has implications for any machine element which is subject to fluctuating loads, right? When they say that an aircraft is going to fly for X number of years, they'll say that it's for so many cycles. So you can predict the number of cycles depending on how many hours it flies. And so you can have like benchmarks or recommendations on when you want to replace parts based on just this curve, provided it's for that material for which you're designing.
So this is just one part.
This
test over and over.
This curve explains for all the cycles. So let's say that you took steel, and let's say this is the curve for steel. It basically tells you that if aluminum is a better example, aluminum is used for lightweight structures. So let's say that you're using it for some machine parts where it's going to be fluctuating load. And then you know that it's going to be subjected to a stress of so much. So that you know, okay, that's going to fail maybe at 5 times 10 raised to 4. So what you'll do is, before it reaches this many cycles over here, you just replace that part with something else. I mean, you replace it with a new one. So then you can start all over again and get it to go these many cycles. So that's how you will probably use this. Yeah. For a material, this is for one material. You'll have to do this for something else. But these are charts which are available in books, so you can just use them to design. SE is the endurance. I'll get to that. It's called the endurance limit. I'll be talking about SE, SUT, and then this all these points in a bit.
It looks like at 10 to the 6, it's like completely failed, right?
10 raised to 6, yeah. So what it's saying is that right over here, this is a strength which it can bear. Okay, so for example, if you are at this much sigma, this is by the way sigma, S is a strength, then it's just saying that you can only go up to this many cycles. If you try to go anywhere more, it will fail before you can take more cycles. But if your stress is now lower to SE, it's called the endurance limit, then you can actually go forever. You can see that it asymptotes. Those two lines, this curve and this line along the x-axis meet at infinity, which means that the part there is never going to fail, provided the load is SE or less than SE. So that SE is a very important number. Yeah. So cycles is units of sort of hertz or one over time. And so you just ask the question, how many times will what is the rate at which the load fluctuates? So if you take, for example, a drone, then that motor, and if it's looking at the motor of the drone, then that's going to be spinning, I don't know, 1,000 revolutions a second, right? That's a very high number of cycles. But then if you take that to, let's say, a train maybe, then it will be 100 cycles per second. It goes much, much slower. So it's just a unit of time. It's actually 1 divided by time is cycles. Hertz as the unit. So then this plot. Okay, so this is, so as I said, we are doing this, keep increasing n and then make a plot of log strength versus log n, which is the cycles. And that's what this plot is. It's a log curve. Sorry, this, my bad. It's S versus, yeah, it's a log curve. And I was just doing a log curve because it looks linear when you do a log curve. If you write it as a strength, if you draw a plot of S versus N, then it will be like a curve. It'd be like an exponential curve, and this is much more intuitive. That's why it's a log curve. This is known as this curve is called Sn curve. And there are other names, but Sn curve is the most common one. So if the cycles are less than 10⁻⁵, it's considered low cycles. And then high cycles are greater than 10⁻⁶. And these are like ballpark numbers, and they came from this plot because we saw that at 10⁻⁵ is the limit where it deviates from being, the slope changes abruptly. And then again at 10⁻⁶, the slope changes abruptly. It becomes 0 after 10⁻⁶, implicating infinite life. Okay, so now this is, as I said, empirical evidence. Now let's use this evidence to make predictions. So what we will do is, from this curve, and by the way, if you take other materials, you'll see that they fail pretty much the same way, except that those points at which they fail, the strength will be different. So here is what is the idealized Sn curve. And it's idealized because we're going to approximate those curves with straight lines. And once we have those straight lines, it's much easier to fit lines, so this is fitting curves. And once we have lines which are fit to this curve, then we can use those lines to make predictions. So this is known as the idealized Sn curve. Okay, so there are 3 regions. This is region 1. This is region 2. And this is region 3. Okay, I don't know if you can see this, but this is SUT. This is called F times SUT, and I'll tell you what F is in a bit. SF, this is SF, and this is SE. Okay, so region 1 is the region from 0, well, actually here it is 1 cycle to 1000 or 10 raised to 3. So this is when the strength goes from SUT, which is the strength at 10 raised to 0 or 1 cycle, to F times SUT. So what's F? F is just a I would say it's like a fudge factor, which basically accounts for the fact that the strength is not going to be constant, but it's going to decrease. And F is typically 0.8 to 0.9. Okay, you find that empirically. And it's kind of easy to find that, to compute that, because you know when the slope deviates, or you know the 1000 cycle line, and so you can compute that. The second region is the one which goes from 1000 to 10 raised to 6. So this goes from stress of F times S UT to SF. Okay, what's SF? F times here. So this should be SE. SE is called the endurance limit. Okay, it's the stress at which at some point of time the life will be infinite. You won't have a failure in this region 3. So 3 is n is greater than 10 raised to 6. So this is commonly known as infinite life region. This is a finite life region in low cycle fatigue region. There are two things here which we need to figure out. What is F and what is SE? Again, so both of them are found empirically, and I'm going to give you sort of equations for them, and these equations again come from plots like this. So okay, so this is how you get SE. So there's something called SE and there's something called SE prime. I'll write in terms of SE prime, and next section I'll tell you what's the difference between SE and SE prime. SE prime is what you see in the test specimen, and SE is what you see in the actual machine element. And the reason why there's SE prime and SE is because the test specimen is idealized, and the actual specimen will have multitude of factors which will change the endurance limit, like impurities and temperature and so on. So I'll write in terms of SE prime, and then I'll fix that SE to SE in the next section. So SE is either 0.5 SUT or 1000 K psi. Okay, so this depends on the ultimate strength, which is obtained from the simple tensile experiment. 200 K psi. Keep it like this. Okay, clearly that one over here is in IPS. Thank you. What if they're in SI units? Well, if they're in SI units, then you would use these expressions. If SUT is less than 1400 MPa, then use 0.5 SUT. If SUT is greater than 1400 MPa, then use 700 is the value for SE prime. This is so this is the difference. SE is for test, for actual machine element, and SE prime is test specimen. So just bear with me. I will talk about the difference. We'll give more details next section. Okay, how they're different and how do you get one from the other. Okay, and I'm going to give you formulas for F. What? There is actually insert. I think I forgot to include this in my handout. Sorry about this. I forgot to include this in the handout, but this is the curve for F. F is a function of SUT. So if you're given SUT, you can just look at the curve and predict what F is. Okay, again, this is empirically obtained. There are some formulas for F, and I'm running out of time. I'm going to write the formulas later in this section, but there are some formulas which give you this line, which I've shown you there, and then you can use the formula, or you can use that plot. Okay, so here it is. F is 1.06 minus 2.8 10 raised to negative 3 SUT plus 6.9 10 raised to 6 SUT square. This equation has been obtained only when the SUT is between 70K psi and 200K psi. So that's the IPS value. And for SI, we have a formula as 1.06 minus 4.1 10 raised to negative 3 SUT plus 1.5 10 raised to negative 7 SUT square, and this holds for 500 to 1400 megapascals. This is IPS. This is in SI. So as I said, compute F either from one graph of F versus SUT or two formulas given above. Okay, in the absence of a formula, you can just assume it to be between 0.8 and 0.9. So most likely you'll be given the value for us.
So when it's outside of those bounds,
Oh, then we don't have a formula yet, but if you want it outside the bounds, then you want to do an experiment and figure out what that function f is. But for most materials in this course, we only are between those bounds. So don't worry about going outside those bounds.
so the question would be like most likely.
Yeah, I'll give you s. Yeah, or you'll have to find f from that plot. Okay, so we've got that, but what we are really after is, if you look at this plot, where did it go? There. So this is the equation of that line, and as I said, that equation is, well, it is not a. It looks like it's a straight line, but how can that equation be SF equals A times n raised to b, right? And that's because this equation, this plot is a log-log plot, and so when you have a log-log plot, that equation is becomes a line. So I can say what I mean by that. If you have, so on the y-axis, we have log s. On the x-axis, we have log n. Right? So it's a log-log plot. And then I'm going to convince you that if you have a equation like a straight line on the log-log plot, it actually boils down to equation of a straight line. So we know that y equals mx plus c. That's the equation of a straight line, right? So this should be the equation of that line. Okay, this and this are the same once you take care of the log. So here's how it goes. So let's sub in the value for y. It's log s equals m log n plus c. Okay, m log n. So how do you combine log n and c? No, it's not time. It should be times, but you can't just combine it, right? So let's assume that this c is log of, let's take this equation and take the log of that equation first, and then we'll be able to relate the two. So log SF equals log A and B, and that product can be written as a sum, right? So it's log A plus log n raised to B, but log A plus, so log n raised to B is B log n. And so now you can easily see that for this equation and this equation to be the same, they're equal, then you need to have what do we need to have? We need to have C equals log of A. I'm just equating the constant, and then M should be B. This M should be B. So if this is the equation of the straight line, then this is Y equals M is B. X plus C is log A. So that sort of convinces us that equation of a straight line Y equals mx plus c, where Y equals bx plus log A. If you convert that to, if you get rid of the logs, you'll get S equals A times n raised to B. Yeah.
Why very specific, like why this curve is a log curve? Any specific reason for that?
Yeah. So what we do is when things become have an exponential type of relationship, like n raised to an exponent, right? N raised to b, you will see that you can always take logs to make that look like a straight line. And I think we have a better intuition with straight lines than we have with something like a times n raised to b. And so you will see whenever there's an exponent taken, they typically write it as a log plot.
Just for the simplification purposes?
Just to make visualizations easier. Straight lines are easier to understand. So this is the equation, but it's kind of deceptive. It doesn't really show you that that's how it comes from. Anyway, so once we have convinced that that's the equation, we need to figure out what that A and B is, because A and B are unknown. They're not related. We know what SF and N is, but we don't know what A and B is. And we need to find those two constants. The way we find the constants is we kind of know where the 2 points through which this line passes through. It passes through this point. So the x coordinate of that point is 1000, right? This one. The y coordinate is f times SUT. And then for this point, the coordinate is 10 raised to 6. And for strength, it's SE. So given a straight line, it has two unknowns, two constants, which we need to find, compute. We have 2 points through which the line passes. We can find those constants. So what I'm going to do is I'm going to find the constants A and B based on the fact that the line passes through those 2 points. That will be taken care when we compute. It will be taken care when we do this substitution to compute. So SF equals A times n raised to B. We know that this curve passes through 1000 F times SUT and 10 raised to 6 times and SE. Let's call this 1, let's call this 2. So I'll substitute 2 in 1. So if you do that substitution, then we have F times SUT equals A times 10 raised to 3B. And then for the second equation, we have SE equals A times 10 raised to 6B. Now, there are many ways to compute A and B. One of them would be just to take the ratio of the two, and you can get B. And then once you have the value for B, you can sub that in one of the equations, and you can compute the value for A. Yeah, just FSUT divided by SE is A times 10 raised to 3B, A times 10 raised to 6B. A is cancelled. We have FSUT equals, or maybe we take the inverse of that, it's easier. So just reverse the order on both sides. F S U T 10 raised to 6b. So that should be 6b minus 3b. 6b. Okay, so take logs. You know, what we'll do is we'll take log to the base 10, and that's just because there's a 10 raised to 3b on the right side. So log 10 3b. So we have a formula for b. 1/3 log 10. So it's important that you, when you use this equation, it's important that you take log to the base 10. Okay. By default, your calculators, I think you have two options. You have natural log, which is the base e, and then log to the base 10. Take to the base 10. Okay, so in order to solve for a, I mean, let me not do that, but the way you get a is, the easier way to get a is to take log of any of those two equations. So for example, log SE from the second equation. Why don't I just do it so that you have it complete? So let's just take log of the second equation. Yes. S equals a 10 raised to 6p. Take log to the base 10. So log 10 SE equals log a to the base 10 plus 6b log 10 to the base 10. You know what log 10 to the base 10 is? 1, right? That is 1. Okay, but we know what the value for b is. It's right here. B is 1/3 log 10 SE divided by F SUT. So that would be 1/3 log 10 SE divided by F SUT. Okay, so this 2. And when we are solving for A, so what we'll do is we'll move this term on the right side to the left side. And then I'll just write it as log 10 A equals log 10 SE minus 2 log 10 Okay, if you have 2 log 10, it becomes SE divided by FSUT square. And then if you have log A minus log B, then you can combine them if you just have to divide one divided by the other. So this would be SUT square divided by SE log 10A. If you have logs on both sides, you can take anti-log of both sides to get A equals F square SUT square divided by SE. So that's it. We were after this expression, we got it. So yeah, it's specific to the region 2. Yeah, absolutely. Okay, so the back. So recap. We have SF equals A n raised to B, where A is given by F times SUT squared divided by SE, and B equals a third log 10 F times SUT. So in region 2, yeah, they are the equation of the straight line, which is it's the equation of this line. Okay, and then the reason why we were after this line is the following: that let's say that okay, we are in that let's say in region 2, and region 2 is a high cycle fatigue region. We want to predict what is the, so let's say that we're given the stress. So the specimen is loaded with a certain load, so we can compute the stress. If you know the stress, can we compute the number of cycles that it will fail? It's a very important calculation because that's how we will design the machine element. So this formula will help you do that. In fact, if you in region 2 given S equals sigma, so let's say that we know the stress, we can compute the cycles to failure as follows. Sigma equals, I'm just going to sub in the value for S there, A times n raised to B. And so n is sigma divided by A raised to B. Where A, B are known. We know A and B because we do know what F is, we do know what SUT is. So we just have to put in the value for A and B, and this formula will tell you what is the number of at what number of cycles this particular specimen or machine element will fail. We have right here.
We just did that.
Oh no, so we did not do that. We stopped at that curve, but we never really got to that. Okay, so I'm going to show you how to use this, what we've developed so far. So here's the problem. Sure. Okay, let's read the question. There's a table associated with the question, but let's read the question. Okay, so we are given a certain type of a steel, H050HR steel. We are asked to estimate the endurance limit at 10⁶ cycles. Okay, what is that? That is basically SE. So since this is a specimen, we are interested in SE prime at 10 raised to 6 cycles. The endurance strength of a polished rotating beam specimen corresponding to 10 raised to 4 cycles to failure. So we're given N. We're told to predict SF, or rather, yeah, strength, SF. And the expected life of a polished rotating beam specimen under complete reverse stress of this. So here we're given the strength, 55 kpsi, and told to expected life is nothing but the number of cycles to failure. So this is part B. This is part C. This is what you have to solve this. So first of all, how do we compute SE prime? I had given a formula. Again, this is all empirical, so there's nothing conceptual about this. The formula is, I think it's right here. You can see that depending on what the ultimate strength is, SUT, you can compute what SE prime is. Okay, so we need to figure out if it is. I believe this problem is in kpsi because one of the questions, part C, we were given the stress in kpsi. So let's just use the IPS units to solve this. Okay, so we have to use one of those two equations. We have to see if SUT is less than 200 kpsi or greater than 200 kpsi. So that can be found from the table. So we are trying to hunt down for the steel 1050 HR. Scroll down. This is 1050 on HR. And then they've given us the tensile strength, that is SUT. This is SUT in both units, MPa as well as kpsi. But since we are interested in kpsi, that's part C is basically something in kpsi. Let's use the 90 kpsi value. This is the SUT. So SUT is 90 kpsi. So let's go back to that formulas. It's under 200 kpsi ultimate strength. So we need to use this formula. So the formula is SE prime is 0.5 SUT, where SUT is, you saw from the table, it's 90 kpsi. So part A. SUT is 90 kpsi. SE prime is 0.5 SUT. Since SUT is less than 200 kpsi. So SE prime is 0.5 times 90, that's 45. Yes, yes.
I mean, in general, let's just say like.
Normally, when you do this, you're usually looking at not a test specimen, you're looking at actual machine element, which will come next time. So for now, just since we have not done any of that material, we'll just do this first. Yeah. So what will happen is you'll see that SE will be adjusted in the next section because it's not the test specimen for that particular instance. So part B is asking us to compute SF for given N. So just use that formula, which goes as SF equals 10, A times N raised to B. N is 10 raised to 4 A is, just look up the value. That's V. That's A. Is the recap. So A is F SUT squared divided by SE. And then B is 1/3 log 10 SE divided by F SUT. Okay, so we have to compute A and B. N is known. For A, we need to get SUT, which we already have, by the way. Now SE is, as I said, it's different from SE prime, but this is a test specimen, so this is the same as SE prime. So we know SE prime. F is not known. So we need to, so what's F? Okay, so we need to now figure out a value for F, and for that we have two options. We can use the formula which I wrote down, or we can look at that graph of F versus SUT. So we know that SUT is 90. So let's just look at that plot. Okay, so SUT is 90. So we read it off here. This should be our F. It looks like it's between 8.5 and 8.6. We want to take 8.855. Let's do that. For Q1. SUT plot. Okay, so we have all those things we need. A is 855. SUT is 90. So this thing should be squared divided by SE, which is SE prime, which is 45. B is 1/3 log 10 SE, which is 45.855. SUT is 90. Okay, we need to compute this. Yeah, that's 131.858, and this one is 0.33 into times log 10 45 divided by 0.855 minus 0.076 776. Yeah. SE is SE prime for SE is SE prime for test specimen. In other words, if you're dealing with an experimental setup where you have that nicely machined element, then SE is SE prime. When you actually go and make a machine element and it is embedded in your machine, that SE for that machine element will be different from the test specimen. And that's because you take so much care in ensuring that the test specimen operates in the ideal lab conditions and loading conditions, and it's machined to the right way. But when you take actually in the machine element, it'll have different, it'll operate at different temperatures. It would have, it would not be perfectly machined, and so on. So there are a lot of factors which make this SE on the machine element smaller or lower in value than this one. And bigger the value, bigger is the load carrying capacity. So no doubt it will reduce the strength because of all those various factors. So I'll come to that in the next section.
So basically this value is like, it's predicted to the point where it's like, it'll work for sure.
It'll work forever. If the load is SC or lower, that part will not fail.
So this SF, like, SF prime. Because the estimate, since we're calculating
Yeah.
it would be different, right?
Yeah, it will be different, right? That's right. Just keep it SF. I think it just makes it more confusing.
Right.
Yeah. Yeah, SF prime is fine. Yeah, so we've got all the equations. And let me just check the value here. I don't have the exact value as I have here because we just assumed an SF. Let's see. So what did I get? I got 16. I got 0.86 for F, which is very close to 855. And then so I got B as minus 0.785, which is close to this. And then I got 131 kpsi, which is close to this. Okay, that's good. Okay, so let's just put that in the equation. So in this case, SF is unknown. A is known. A is 131.58. N is given. B is we computed B, so that's minus 0.0766. It's actually 776. $64. 64.39. That's kpsi. Okay, the last question. Here we're given the stress and we're asked to compute the number of cycles to failure, which is more like the design question we're after, right? It's because the machine element is going to be, or the test specimen is applied a stress, and we are told to compute what cycles it will fail. So I use the same equation. So part C. SF equals A n raised to B, where SF will put sigma now. Then n is sigma divided by A by B. So I'm going to sub in the value. It's 133. That's right. 55, my bad. 55 for sigma. A is 131.58 and B is minus 0.0776. Okay, I get 77.6172 times 10 raised to 4. It's better written as 76. Or we can round wherever we want to. So 1, 2, 3, 4. Just make it a little higher, right? 76. Let's just make it 771 cycles. So 77,000 cycles